Hello, my name is Kaylin Maher. The title of my video is Free Energy in Thermodynamics, Solving for the Number of Microstates in a Given System. I will be solving problem set number 7, 1A and C. The problem asks how many microstates are in the following systems: a molecule of hydrogen gas and 5 molecules of chlorine gas. A microstate is defined as a unique arrangement of molecules or particles. In other words, each snapshot of a molecule is one microstate. To solve this problem, we use Boltzmann's equation. Boltzmann theorized that the entropy of a system was related to the number of different ways particles could be arranged. Boltzmann's equation is written here. S equals Kb ln W, where S is the entropy in joules per Kelvin, W is the number of microstates, Kb is Boltzmann's constant, or 1.38 times 10 to the negative 23rd joules per Kelvin, and Kb is obtained from R divided by Na, where R is equal to 8.314 joules per Kelvin, and Na is Avogadro's number, 6.022 times 10 to the 23rd. Let's start with problem 1A, the number of microstates for a molecule of hydrogen gas. To begin, I started by isolating W. W, as mentioned earlier, is the number of microstates. Divide S by Kb, and then do e to the S divided by Kb power and e to the ln W power. E and ln W cancel out, and so W is equal to e to the S divided by Kb power. Next, I obtained the S value, or entropy, from the appendix of the textbook. S of hydrogen gas is equal to 130.7 joules per mole Kelvin. To find S for one molecule, we multiply our S value by 1 mole divided by 6.022 times 10 to the 23rd molecules. This gives us the value of S for one molecule, which is equal to 2.170 times 10 to the negative 22 joules per molecule Kelvin. And in order to prepare the units for the next part of the problem, I multiplied by 1 molecule of hydrogen gas, since the problem asked for 1 molecule, to get an S value of 2.170 times 10 to the negative 22 joules per Kelvin. I then plugged this S value into the equation on the left side of the screen, where I isolated for W and used Boltzmann's constant to solve for the number of microstates. When plugging in these values, you get W equals 6.689 times 10 to the 6 microstates per hydrogen gas molecule. I used 4 significant figures for my final answer because the value obtained from the appendix of the textbook had 4 significant figures. For 1C, you follow a similar set of steps. You isolate W again, as shown on the left, and I'll just repeat how to isolate W. Divide S by Kb, and then you do e to the S divided by Kb power is equal to e ln W, and then your final equation is W is equal to e raised to the S divided by Kb. We are isolating W because, once again, we are solving for the number of microstates. For problem 1C, we obtain the S value from the back of the textbook as well, which is going to be 22.31 joules per mole Kelvin. And we multiply by 1 mole divided by 6.022 times 10 to the 23rd molecules, just as we did in the first problem. However, because 1C asks for the number of microstates in 5 molecules of Cl2, we then multiply this value by 5 to obtain our final S value of 1.852 times 10 to the negative 21 joules per Kelvin. Using the equation above where we isolated W, we plug in our S value and Boltzmann's constant to get a value of 1.791 times 10 to the 58th microstates for 5 chlorine gas molecules. We also use 4 significant figures for this problem because the S value obtained from the back of the textbook limits us to 4 significant figures. To summarize, the problem asks for the number of microstates in a given system. A microstate is a unique arrangement of molecules or particles. To solve for the microstates, we used Boltzmann's equation and isolated W. Then we plugged in our S value and Boltzmann's constant to solve for a value of W.